Today we will discuss about the differences between small signal amplifiers and large signal amplifiers. We know that an amplifier is going to be an electronic device which amplifies the strength of a weak signal without distorting its wave shape. Amplifier means which has amplification without distortion in its wave shape. Let us assume we are going with an amplifier gain A. The input signal, if you are applying sinusoidal, you must get a sinusoidal output only, but with larger magnitude. That is what the function of amplification, function of amplifier. So basically amplification is going to be measured in voltage gain or current gain or power gain. Gain is nothing but a ratio of output quantity to input quantity. Based on the quantity of interest, it may be voltage gain, current gain or power gain. So voltage gain can be defined as output voltage by input voltage. And we know that one BJT is going to be acting as amplifier, and BJT either it can be PNP or NPN, which consisting of three terminals: emitter, base and collector as indicated. And we can differentiate whether it is PNP or NPN based on the arrow direction. If the arrow goes in, at that time PNP; if the arrow goes out, it is NPN. Can a BJT act as amplifier? If you apply the input signal to the amplifier directly. So if you are going to apply like this is a transistor, let us assume it is acting as amplifier. By that time, if you apply the input signal directly to the base and emitter as in this way, are you going to get amplification at the output terminal, collector, with respect to emitter? That is, V out is going to be an amplified version of input signal or not? There is no amplification will be provided if you simply apply the input signal directly. So we don't get any amplification. If you want to get amplification, at that time transistor must be biased in active region. So BJT act as amplifier whenever it is biased in active region. So how to keep the transistor in active region? And before that one, what is meant by biasing? Biasing is a process of keeping the transistor in one of its operating regions. It may be either active or saturation or cutoff region. So placing the transistor in one of the region is going to be called as biasing. And there are three different regions, operating regions, that is active region, saturation and cutoff. Whenever the transistor is biased in active region, it can act as amplifier or oscillator. Otherwise, if you want to make applications for the amplifier as well as oscillators, at that time BJT must be biased in active region. Similarly, if you want to make use of BJT as a switch, at that time it must be biased in saturation region and cutoff region. In saturation region it acts as on switch, in cutoff region it acts as off switch. So how to ensure the transistor is going to be in a desired operating region? And we know that every transistor consisting of two junctions. One is emitter base junction, the other is collector base junction. So based on these two junctions implies nothing but PN junction is nothing but simply a diode, which can be either forward bias or reverse bias by applying the voltage across it. So when there are two junctions, there are four possibilities you will get. Both may be forward bias, both may be reverse bias, one may be forward bias, by the time other can be reverse bias. So all these four regions, four possibilities are listed out here. JE implies nothing but emitter base junction, JC collector base junction. If JE is forward bias and JC is reverse bias, that is emitter base junction forward bias, collector base junction reverse bias, then the transistor is said to be in active region, where it finds applications as amplifier as well as oscillator. When both the junctions are forward bias, at that time BJT is said to be in saturation, where it can act as on switch. When both the junctions are reverse bias, then it will be in cutoff region, and where it finds application as off switch. Whenever emitter base junction is reverse bias and collector base junction is forward bias, at that time it is called as inverse active region or reverse active region. and where it doesn't find any applications. Generally, BJT is called current control device. Current control device is nothing but output current is controlled by input current. So you must able to apply input current such that it can be amplified and your output current you will get. But if the input junction, that is emitter base junction itself, is going to reverse bias, under reverse bias no current flows, that is no more chance of application of input as signal, so it doesn't find any applications. Now active region means emitter base junction forward bias and collector base junction reverse bias. If you make a transistor's emitter base junction forward bias and collector base junction reverse bias, by that time we can confidently say that one BJT, that is transistor, is an active region. Now we will see what are the possible things. A simple way of making it is nothing but this is a circuit. Here this is emitter base junction and base is, it is arrow is going outwards, that is NPN transistor. For NPN transistor, base is of P type, so base and emitter is going to be forming a PN junction, and base is more positive, that is P side is more positive than N side, that is emitter side, so that emitter base junction is forward bias, and by applying VCC is going to be more than VBB. We can say that one collector side, that is N side, is more positive than P side, so that collector base junction is going to be getting reverse bias. So by using these two power supplies and two current limiting resistors, we can keep the transistor in active region by ensuring that emitter base junction is forward bias, collector base junction is reverse bias. But the disadvantages of this circuit are, it requires two power supplies and there is a problem of thermal runaway. Thermal runaway means self-destruction of transistor as the temperature increases. Third one is poor stability. And the best biasing circuit what we have studied is nothing but voltage divider or potential divider or self-biased circuit. This is what that circuit. With the help of power supply, single power supply VCC and R1 R2, these two resistors are forming as a voltage divider, and RE is going to be acting as feedback resistor, which eliminates thermal runaway problem, so that this is the best biasing circuit. And since you are applying constant voltage and resistor values which you are not changing, that is they are also constant, what we expect is nothing but constant currents are flowing in the transistor. Those constant currents are going to be called as DC currents or quiescent currents, and because of that one there will be a constant voltage across the transistor terminals. They will be called as DC voltage or quiescent voltages. So these are the two important parameters of transistor. One is collector current IC, which is function of base current. So IC can be written as beta times of IB, and VCE can be written as VCC minus IC times of RC plus RL. So this equation is little bit wrong. VCE is equal to VCC minus IC times of RC plus RE. RC means the resistor connected collector. This is. So these two parameters are going to be called as operating point or Q point. It is written as Q of VCE comma IC. If no AC signal is applied, then all these currents IB, base current, collector current and collector to emitter voltage VCE, all are going to be constant. So constant is nothing but the value doesn't change with respect to time. We can write the waveform in this way. Constant base current in microamperes, constant collector current in milliamperes, constant collector to emitter voltage VCE in volts. All are constant since we are not applying any AC signal or input signal. Let us assume we are applying the AC signal. Then the base, collector and collector to emitter voltage VCE are going to be changes with respect to their DC values. Already because of DC voltage they will be at some values. If you apply AC signal such that the AC signal is increasing, at that time IBIC may increase. such that the AC signal is going to be decreasing. IC may decrease. So this is what the circuit used to apply AC signal. V input, and it is C1. Through C1 we are applying, so that if this input signal is going to be having some DC component that is blocked by this capacitor, so Q point of this transistor remains stable. So whenever we are applying a signal V input and that is superimposing on the base terminal, so that this base current will get changed. There will be variations taking place at the base. So let us assume the variations are such that they are going to be taking sinusoidally. So now the base current is going to be changes from its DC value, that is IBQ, in this manner, and IC is a direct function of IB, so that IC is also increases and it maintains the same wave shape as IB, like this. But the only difference is IB will be in microamperes and IC will be in milliamperes. IC is equal to beta times of IB, and VCE is nothing but it is going to be decreases. This is the manner. VCE is equal to VCEQ. As IC increases, voltage drop across the load resistor is going to be increases, so that voltage from collector to emitter effectively reduces. So this will be taking this shape. Now whether the amplifier is small signal or large signal, that is going to be defined based on the variation of base current with respect to its DC value. How the base current is going to be, how much the base current is going to be varying from its DC value, based on that one it is defined as whether it is small signal or a large signal. So based on the variation of input base current with respect to its DC value, there will be two cases, small signal and large signal. Let us assume we are going with small signal. First we will take case of, in small signal, the variation of base current from its DC value is shown in red color, and variation of AC is going to be taking blue color. So this is the total current. Blue color is nothing but total current, which consisting of AC plus DC. So base current is going to be of variation very small. If you observe, there is a variation of only 1 microampere, which is very small compared to its DC value, which is 10 microamperes. So IB maximum is nothing but 11 microamperes, IB minimum 9 microamperes, DC value of IB is 10 microamperes. Now if you check the variation is around 1 microampere. Here it is not milli, it is 1 microampere, which is very small compared to your DC current. So such type of amplifiers are called as small signal amplifiers. Whereas if the variation is very large at the base, that is nothing but like this. Now you see, the variation is very large from its DC value. So by that time, the maximum excursion can go towards 19 microamperes, or the minimum excursion may go towards 1 microampere from its DC value of 10 microamperes. The variation of base current from its DC value is around 9 microamperes, which is very much comparable with its DC value. This type of amplifiers are going to be defined as large signal amplifiers based on the excursion of base current from its DC value. So small signal amplifiers, in small signal amplifiers the variation of base current from its DC value is small, and because the variation is small, even though it is gets amplified and appear at the collector current is always will be in the active region. It never goes into saturation or cutoff region. So transistor collector current will always be in active region, and it maintains a linearity, that is IC is always proportional to IB. That's why transistor is going to be acting as linear element in small signal amplifiers. Whereas in large signal amplifier, base current variation itself is going to be very large. Whenever it is gets amplified, at that time it appears as collector current, and the collector current may go into saturation or cutoff region or both also. By that time, whenever it goes into saturation region, at that time positive portion of collector current will get clipped off. If the collector current goes into cutoff region, by that time negative portion will be clipped off. So that makes the distortion to be appeared at the output waveform. In large signal amplifiers, distortion appears. In small signal amplifiers, distortion is not there. So distortion is appearing in large signal amplifier is nothing but it acts as non-linear element. Transistor behaves as non-linear element in large signal amplifiers. We will see one more important difference. In small signal amplifiers, transistor is acting as linear element, so output is directly proportional to input. V0 is proportional to V input, so we can write as V0 is equal to K times of V in, where K is equal to gain of amplifier. So if the input signal, let us assume we will apply some input signal, that is sinusoidal signal will apply. So what can be the output, that we will see. Let us assume V input is equal to cos omega 1t, that is cos 2 pi f1t. So a sinusoidal signal of frequency f1 we are applying as input. By that time output V0 can be written as K times of V input, K times of cos 2 pi f1t. Observe the frequency component present in input and output. In input there is a frequency component f1, and in output is also same frequency component f1 you will get. So that implies nothing but there is no change in the frequency component, same frequency component, only the magnitude is going to be increases by K times. So that implies nothing but the wave shape is going to be preserved at the output side. Whatever you are applying at the input side, the same wave shape is going to be preserved and it appeared in the amplified version. So input wave shape is preserved at the output side. What happens in case of large signal amplifier if you apply the same input signal? We know large signal amplifier transistor act as non-linear element. General nonlinear equation is going to be defined like this: V0 is equal to A1 times of V in plus A2 times of V in square plus A3 times of V in cube. Like that we can write, we can extend, where A1, A2, A3 are going to be treated as constants. Apply the same input signal as cos omega 1t, that is cos 2 pi f1t, a sinusoidal signal with frequency f1 we are applying as input. Then we can write the output as A1 times of cos omega 1t, A2 times of cos omega 1t square plus A3 times of cos omega 1t cube. So if you observe the frequency components in input and output, in input there is only one frequency component, that is f1, but in output there are so many other frequency components along with f1. So if you are cleanly observing A1 cos omega t cos omega 1t consisting of one frequency f1, cos omega 1 whole square is nothing but cos 2 omega 1 minus 1 you can write, that consisting of 2 omega 1, that is 2f1 frequency component. Similarly cos omega cube is going to be consisting of 3 omega, and similarly 4 omega, 5 omega, like that also you are getting frequency components. So output consisting of integer multiples of fundamental frequency f1 along with f1, that is V0 consisting of f1, 2f1, 3f1, 4f1, like this frequency components. So we can say V0 consisting of fundamental frequency f1 and harmonics. Harmonics is nothing but integer multiples of fundamental frequency, that is 2f1, 3f1, 4f1. So because of these harmonics output gets disturbed, that is there will be distortion in the output signal. This type of distortion due to harmonic components, harmonic frequencies, is called as harmonic distortion, which is present in large signal amplifiers, which doesn't find in small signal amplifiers. This is the one more very important difference. So in large signal amplifier output gets distorted because of harmonic frequencies. This referred as harmonic distortion. So apart from the previous differences, now the other difference is nothing but harmonic distortion is present in large signal amplifiers, whereas harmonic distortion doesn't present in the small signal amplifiers. Next, examples for small signal amplifiers are nothing but voltage amplifiers, whereas examples of large signal is nothing but power amplifiers. Applications of small signal amplifiers. All stages in a multi-stage amplifiers are called as voltage amplifiers except last stage. In multi-stage amplifiers except last stage, all stages are going to be treated as small signal amplifiers only, that is all voltage amplifiers. Large signal amplifiers. Last stage of multi-stage amplifiers is always power amplifier. Last stage of multi-stage amplifiers, here please write it, last stage of multi-stage amplifier is always power amplifier. And small signal amplifier is nothing but transistor acting as linear element, and it is analyzed, that is calculation of voltage gain, current gain, input impedance, output impedance, all these things are going to be performed using H parameter model or R parameter model. Whereas for the large signal amplifiers, the analysis, that is nothing but calculating the efficiency, power efficiency, how much is going to be the DC output power, how much is going to be the AC output power, the ratio of that one. All these things are going to be analyzed using the graphical technique. So the basic differences are going to be small signal amplifier is nothing but the variation of base current from its DC value is very small, so that collector current always vary within the active region, that makes no distortion in the output signal, and so that linearity is maintained, no harmonic distortion present. Examples are voltage amplifiers. Applications are all voltage amplifiers, that is all stages in the multi-stage amplifiers except last stage, and analysis is performed using H parameter model or R parameter model. In case of large signal amplifiers, the variation of base current from its DC value is very large, so that the collector current is also gets large after amplification, and by that time it will be limited by its saturation and cutoff regions. So collector current enters into saturation region where the collector current is constant. It no more responds for the changes in the input. That's why positive portion is going to be clipped off whenever the collector current enters into saturation, and whenever the collector current enters into cutoff region, by that time again it doesn't respond to the input changes, so it becomes zero ideally. So negative portion of input waveform will be clipped off whenever the collector current enters into cutoff region. Because of that one, distortion appears in the output waveform, and this output waveform, so that we can say that one transistor is acting as nonlinear element, and nonlinear element always produces harmonics of fundamental frequency. Because of these harmonics, the output is going to be gets clipped off. So harmonic distortion is present in large signal amplifiers. Examples of large signal amplifiers are power amplifiers. Application is nothing but always the last stage of multi-stage amplifiers is always power amplifier, and analysis is going to be calculated using graphical technique, that is calculating the maximum power efficiency, how much total harmonic distortion, what will be the AC power output. All those things can be calculated using graphical technique. These are the basic differences between small signal amplifiers and large signal amplifiers. Thank you.